10 gigahertz, that is radar, kappa E is about 78. So that means the speed of radar in water is 1/9 roughly of C. So it's only 10% roughly. It's 10 times slower. If we go to visible light, so this is the radar, and this is of course even lower frequency that goes through the radio. If you look at visible light, you may say that light by definition has to be visible. Well, we physicists make a distinction between light in general, which is all electromagnetic radiation, and a certain part of the spectrum that we can see. And that's what we call the visible part. So that's visible light, which has a frequency of very roughly 5 times 10 to the 14 hertz. It's huge. And kappa E there is roughly 1.77. Look at the enormous difference. At that very high frequency, the electric dipole of water cannot follow the changing electric field. And therefore, it just sits there and it has almost no impact. And that's why the number is so low. So that means that in water, visible light has a speed which is about 30% lower than C. That is dispersion. And later in the course, we will see how a prism made of water or made of glass makes it possible to decompose white light into colors. That is only possible because of dispersion. That is only possible because the speed of light for blue light is different from the speed of light for red light. We will also explore in 803 the transport of electromagnetic waves through metal pipes. We call them waveguides. Here I have a metal pipe. The opening here is about 1.5 centimeters across. Light has no difficulties getting through. I can look at you, and I can see you, and I can see you. You may be able to see me, I don't know. I have no problems. Light has no difficulty getting through here. But radar, with a wavelength of 3 centimeters, would have great difficulties getting through here. I will derive in the future what happens with radar when you send it through metal plates. You will see a dramatic example of dispersion. And this is a result of the boundary conditions of the electromagnetic waves with the pipe. But I want to tell you the result, because it is such a remarkable example of dispersion, and I want to demonstrate it to you, because it's very relevant in this lecture, because it all comes down to dispersion. We have there 2 aluminum metal plates that you see there. Here is one, and here is the other. Let's call this the direction of Z, and let's say they are a separation A apart. So that's the separation between them. We have a 10 gigahertz transmitter, which is a radar transmitter here, and here we have a receiver, which can receive the 10 gigahertz. And so we're going to send it from here to the other end. The wavelength, lambda, is 3 centimeters, so this is 10 to the 10 hertz. So lambda is 3 centimeters. When A is less than 1.5 centimeters, radar cannot go through anymore. If it's larger than 1.5 centimeters, it can, and I will demonstrate that. But what behind that is, and that's really what I want to get across, is the dispersion relation, which I will derive, but not now, but I will derive it a few weeks from now when we reach that point. But I want to show you what that dispersion relationship will be if we have done our homework. Omega n, whereby n equals 1, 2, 3, 4, 5, equals C times the square root of n pi divided by a squared plus k of z squared. Let's first look at this term. Even though you don't see directly where it comes from, you can connect to it already. It has to do with boundary conditions. Remember when we had a string that was fixed at both ends, we got terms like this. Remember when we had sound in a box, we had n pi divided by L in the x direction, m pi divided by L in the y direction. So you recognize here that it has to do with the boundary condition of the electromagnetic radiation without exactly understanding why it is the way it is. And so the phase velocity, v phase, in the z direction is omega divided by kz, and the group velocity in the z direction is d omega d kz. I will concentrate now only on the case that n equals 1. So I make this a 1 because that gives me the lowest frequency possible in this dispersion relation. And I'm now going to graph that thing, omega versus k, omega versus k. This is non-dispersion. I can write here omega equals kz times c. That is the case when k is huge, very short wavelength, way shorter than the dimension of the pipe. Then that system acts like a non-dispersive medium. You're somewhere here. But if you go to low frequencies, this is the curve. And what you see here, there is a value which we call the cutoff frequency omega. It's normally called omega c, below which no radiation can go through the pipe. This is not a solution anymore to my wave equation. You're stuck to this line for the mode n equals 1. So what is required that the frequency for this radiation, well, first let me give you what omega minimum is. Omega minimum is when you make, in the extreme case, kz 0 and n equals 1. So you get c pi divided by a. That is the minimum value for omega that can propagate through these two plates. And so a required frequency is that f is larger than c divided by 2a. That means a has to be larger than 1.5 centimeters. And that is so non-intuitive. And this is what I want to demonstrate to you. So we have there those two plates, and the plates are now something like 2 centimeters apart. You can check this after the lecture. We modulate the 10 gigahertz with a nasty triangular sound of 550 hertz. And the reason why that is nasty, because you now understand that anything that is modulated triangular requires high harmonics, because think in terms of Fourier space, and higher harmonics not so nice in your ears. So if this were a nice sinusoid, you would hear a beautiful 550 hertz tone, but because we modulate it with a triangle, it's a nasty tone. But the only reason why we want you to hear something is that when this receiver receives the radar signal, we want to hear this modulated signal. Unfortunately, you and I cannot hear 10 gigahertz. Our ears are not designed to follow a frequency of 10 billion hertz. It cuts off at 20 kilohertz, as you remember. So we're going to show you this transmitter first. The transmitter is the signal upstairs, so it is 10 gigahertz, but it is a triangular modulation, which is 550 hertz. Here is the receiver. When I turn on the receiver, you will hear that signal coming out here. And at the bottom, you see the signal received by the receiver. And the fact that it is a little larger than the upstairs is simply a matter of how we adjust our amplifiers. Nicole, can you be my witness and look here so that you can tell class what I'm doing? I'm going to take these two plates now. Yeah, please come up here and just watch here and tell them that what I'm doing is completely honest. You see the opening here now of these two plates? And these plates are about 1.8 centimeters apart, almost 2. And now I'm going to make it a little less than 1.5 centimeters. Watch there and listen. It's gone. It's completely gone. And would you tell class that the opening is still sizable, right? The opening is just a little less than 1.5 centimeters. And it instantaneously goes away. There it is. Why don't you squeeze it, Nicole? And it's gone. Thank you, Nicole. You were expert. Now, there is one more thing that is important, and that has to do with your sleepless nights. Because you know I'm very concerned about you getting enough sleep. Look at that dispersion relation. Look at this curve. This line indicates the speed of light c. That line indicates that when omega divided by k is c, that's the speed of light. So what now is the phase velocity, for instance, at this frequency, so that has this value for k? Well, it's this. This slope is larger than this one. It's higher than the speed of light. Not only is it higher than the speed of light, the phase velocity, but by the time I reach this point here, the phase velocity goes to infinity. Because look at this slope, it's 90 degrees. So we now have a case that the phase velocity is larger than c. No, the phase velocity can be much, 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 much larger than c, approaching infinity. And what now is the group velocity when we reach this point of the cutoff frequency? That is the tangent. And so this is the slope of the group velocity. So the group velocity goes to 0 in that extreme case. I sure as hell hope that you can sleep tonight.